So welcome everyone. Our speaker today is Konrad Tywoniuk. He will talk about community detection by simulated bifurcation. So please go ahead and present.
Thank you, Franz, for a nice invitation. And it's nice to talk on the first day of spring this year. So the talk is community detection with simulated bifurcation, and it's based on the paper written here on the slide. I will try to explain a bit about the different words in this title. The outline of my talk is going to touch upon what is quantum optimization, then I will focus on oscillator networks and in particular simulated bifurcation. What is that? And finally, the application is community detection or some kind of clustering problem. And I'll show some results at the end. So I'll try to not go over time. So quantum optimization, of course, is very closely linked to the physics problem of finding the ground state of a system, described by, in particular, a Hamiltonian, which is the energy function. And the kind of most typical one that we talk about is the one that I wrote here, which is the Hamiltonian of an Ising model, of a generalized Ising model, where the S's are spin variables and the Jij are coefficients are couplings between the spins, and kind of H is the external magnetic field. And the reason why I wrote this particular Hamiltonian is that, of course, there is an equivalence between the Ising model and a large class of combinatorial optimization problems, those that can be basically formulated as so-called quadratic unconstrained binary optimization problems. So, of course, we know very well the structure of the Ising models, at least when you have nearest neighbor interactions and some well-structured lattices. But when you have a typical graph problem, you can have all-to-all connections, complicated connections, and things like that. So there's an equivalence, but there are also new challenges arising to kind of solve kind of these kind of Hamiltonians with a graph problem in mind. And examples and benchmark for such graph problems are, of course, max cut problems, or clustering problems, community detection. But of course, the general class of systems that recently also have been very popular to think about are spin glass problems. Can we have algorithms? Can we have computers? Ways to solve very tough and complicated spin glass problems, finding basically the phase structure of this Hamiltonian and phase structure and the ground state as a computational benchmark. So these are both interesting in the terms of physics. You can learn something new, but also from the point of view of optimizing real-world problems. And there is a vigorous activity on this in this field, both on the hardware side, where here I show the D-wave quantum annealer, which is a sort of a quantum machine where you have quantum degrees of freedom that can solve such problems. And also you have a lot of similar optimized solvers or hardware solvers. For instance, the Fujitsu digital annealer and other machines, so-called Ising machines in general, that are specifically optimized to solve the Ising model and its generalized variants. So there's also a lot of activity on algorithms. So not only on the hardware, but also algorithms that can lead to new ideas, lead to new solutions. The thing is to do this efficiently, reliably, and also as fast as possible. That's from the point of view of optimization. But there is still an ongoing debate whether what is the role of quantum effects, real quantum effects, and what is the role of simply smart algorithms, classical algorithms. So recently, last year, D-Wave and collaborators posted a new paper on setting up exactly computational benchmarks for quantum simulations or quantum optimization in narrower sense, perhaps. And those are exactly some kind of spin glass problems in a sense on different types of lattices, etc. But there's still an open debate, an open question whether the advantages that you can see in, for instance, D-Wave or other types of quantum simulations are related to the quantum nature of the simulation, or there could be also smart, efficient classical algorithms that can do a very good job. So here there's an answer from this year, where you can do classical simulations of annealing dynamics. So the whole context of my talk is exactly this kind of annealing dynamics, finding the ground state by mapping out the phase structure if you want, but basically it's about kind of cooling the system or relaxing the system to the ground state of an Ising model. So the framework we have been working in is related to oscillators, and in particular parametrically driven oscillators. Oops, sorry about that. Here in the Hamiltonian that I've written out is the Hamiltonian for a so-called Kerr parametric oscillator. So the third term here in the Hamiltonian is the normal oscillator behavior with the annihilation operators and creation operators. But then you have two additional terms, which are the first and the second term are basically the nonlinearities of the Kerr oscillator, and then a driving term P with P. And the last term is the coupling between different oscillators, which we'll leave for the moment aside. Let's focus on the first term first. The reason why this is a very interesting system is that you can induce a bifurcation property. So by increasing the nonlinearity, the P parameter, as we can see in the A and B inlets here, the figures, so the X variable is the position and the Y variable is the momentum, which is of course related to the creation operators and annihilation operators, as we know from quantum mechanics. So basically what we can see is that in X, in the position space, the oscillator basically at low nonlinearities is in its normal, oscillates around its normal ground state, but then at the critical value of the nonlinearity parameter, it bifurcates either into one solution or into another branch. So that's a fantastic, interesting property, and that is also mirrored into quantum dynamics. So you can see downstairs in the figures C and D, the Wigner function. So it's basically kind of the quantum equivalent of the upper plots, where you see the Wigner function at strong values of nonlinearity on the right. You see that the Wigner function, instead of kind of being located around the minimum around 0, it basically bifurcates into two different stable points. And so in the quantum world, this is a so-called Schrödinger cat state. So you don't really know. Classically, the system will either go into one or the other minima, but quantum mechanically, it kind of is quantum mechanically in the superposition of both. So that's a very interesting, and this is actually experimentally realizable. You can have junctions, you can have so-called memristors or other types of devices that can actually realize this kind of oscillator-driven oscillator, parametric oscillator properties. Now, for the last term of my Hamiltonian is exactly the coupling between oscillators. So the idea is that as you kind of couple these oscillators together and you drive them with a dependent coupling, when you drive them through their bifurcation points, you will end up at in a very rich landscape of a lot of that explores the minima of the whole system of the n and oscillators. So you will explore all the minima of all the oscillators. But of course, the idea is to kind of realize this in a real quantum device, but that might be a kind of a very daunting, challenging problem. So what we have been working on is, of course, much simpler. It's a classical algorithm. That is a classical approximation to the full quantum dynamics. It's basically we neglect a bit of the dynamics. So you can ask me later for the details, but it's more or less the classical equivalent. So in a sense, it's not a quantum superposition state, CAT state, but it's basically a dynamically driven, then through the bifurcation points of all these oscillators, a classical set of oscillators. This is solved two ways, where ballistic and discrete versions of this. This is just numerical kind of details, but the thing is that this algorithm allows, so since it kind of is a set of basically classical equations of motion, you can update all the variables at each time step, and that allows for massive parallelization and massive time saving. So it's not like in a Monte Carlo simulated annealing or something like that, where you pick up one in one spin, or you have some smart way of picking up more perhaps, but it's really a way to parallelize the whole system at the same time. Here I add the formulas, but I won't go much into the details. Here, what I just wanted to actually show in this figure is the lower right plot, where you see actually, in this case, from this paper down here from 2019, the conference proceedings, it's how the Ising energy decays with the step counts. And you see that initially all the oscillators are kind of in some kind of initial state, random state around zero. And then as the time goes, the oscillators are either being driven through their bifurcation quite violently into either of the minima. But of course, what's interesting is still that after several steps, you can still flip a lot of degrees of freedom, it seems. So in the end, these are also important to remember, that these are classical variables. But in the end, we'll just take the sign of the classical variable, so whether it went into one minima or the other. But the fact that they are classical also gives us some kind of richness, we believe, that you kind of you're not really in one kind of quantum defined state, but you're in a classical continuum of values. So finally, to our problem, we decided to go for community detection. It's a very interesting problem from graph theory, a NP-hard problem. And of course, it's about finding patterns in large-scale networks, also to divide them up into more manageable parts. We see here two kind of examples. There are many more, but this is basically the pages, the websites and hyperlinks of one. I think it's one website basically with the many hyperlinks and things like that. And also down here, an interesting application for us is power networks, energy networks where electrical energy is being sent around. So this is the German network, kind of global view of it, not of course the local view. But what one see here is that those kind of clusters can be complicated and non-trivial. And these are the clusters where we believe perhaps the energy would be redistributed in the most efficient way without losing too much power, without losing too much on these different losses in transmission and etc. So what we kind of also worked with is what's called, somehow has been dubbed the electrical distance, which is somehow a weight that tells you how much resistance is along a transmission line, and also the reactance, so basically how much energy you lose inside of each node when the energy passes the node. So so this is how we kind of set up that problem for electrical grids. And this is a very super interesting application, I believe, for other studies as well. But the way we approach this problem of community detection is through the so-called modularity. So modularity matrix is defined in the upper right here, where A is the adjacency matrix. So basically how these different nodes talk to each other, so to speak, how far they are from each other, or how close in some way. And the second term is basically should represent a kind of a random graph, but it's not completely random graph. It's kind of your own graph. So Ki is what's called the degree of node I. So it's basically just a random graph. If your graph would be completely random, it would kind of look like just a product of those Ks. That's one way of thinking about it. So it's how different is your graph, your adjacency matrix, from just a random connection, but not completely random. But without structure. Let's say a typical matrix without structure. So this is in order to kind of not completely compare your graph to a random graph, but to an equivalent graph where there is no specific communities. There are no specific communities, and the way we kind of then we sub up over all nodes and basically count all nodes that belong to the same community up, in a sense. So this is very similar, not to the Ising model. In fact, this is very similar to the Potts model, if you know that. So large values of M then basically indicate good partition. So if you have low values, that means that the graph is basically a random connections and no specific structure in it. And there are also many interesting things here to do with this. But let's go on. So we want to basically maximize this kind of modularity. Acts as our Hamiltonian or energy function or loss function. Where now, instead of treating it like a Potts model, we basically extend our binary vector into kind of with two indices, so that the first index kind of is the node index. So 0, x00, so the first 0 will be the node number 0, and the second index whether the node 0 belongs to cluster 0. And x01 would be the 0 belongs to, or not belongs to cluster 1, etc. This is the thing. Of course, we have to enforce two constraints here. One constraint is that each node has to belong to one community. So this is the one we choose. There's no overlapping communities, in a sense. So one node has to belong exactly to one community. So when we sum up of all communities, then that particular node I, has to belong to at least to one of them, not to more of them. And the other constraint is that every community has to have at least one participant, or else we would have a lot of communities with just empty communities without any participants, any nodes. So the second soft constraint, what I refer to as a soft constraint, is a bit tricky to enforce. I just give you the slide here how we do it. We have to actually enforce it kind of that instead of actually being bigger or than 1 or equal than 1, we say that it's equal to some number, and the number is adjusted on its own, in a sense. So it's equal to some number bigger than 1, but that number adjusts itself, and that is being done through these so-called slack variables. So the slack variables are again binary variables, those x, d, k, and they're basically adjusted so that this combination of the slack variables gives you a number that is between 1 and a big number. So that's also in this formula you also see. So we have to adjust the number of slack variables, and we also have to adjust the so-called penalty multipliers alpha and beta to kind of enforce these constraints so that we don't break them. We don't get non-physical solutions, in a sense. And at the same, so we have to, this is some kind of a Lagrange multiplier, and we have to minimize this whole function here. So let me come to our results. Maybe I'm rushing a bit, but let me have more time for discussion. Then, so we focused on kind of small and intermediate graphs. Because it turns out, of course, that when you have both the slack variables and you also allow for many clusters, then of course the number of your variables increases quite a lot, and the problem itself, the dimension of the problem becomes very quickly enormous. So, for instance, for this Zachary's Karate Club example, where we have kind of 33, 34 members that are being divided into cliques, into groups, competing against each other somehow, sociological groups. Then in the end, when we compute many big number of communities, etc., we get a huge solution space type of like of the order of 10 to the 29th. So this is actually a vast problem. Even if the number of nodes is small, the solution space is huge because of this complication. And so we have run this. So what you do is that you try out different sizes, different number of communities, and how these different communities optimally would work, and you find the optimal one. And the good news is that our algorithm gives a very good number of better than the let's say IBM result. It's not to pound on IBM, but IBM, this paper is basically a paper using another technique on a quantum computer, IBM computer. Of course, the D-Wave is also a quantum computer, highly specialized, a huge machine. And the Fujitsu digital annealer also is a huge effort to build such an optimized machine. And our code runs on our computer, on our laptop. So it basically shows that the SP algorithm has a very nice property, and this is not something we understand completely, right? But we see the features, we observe it, and we have tried it out on this example here, and we see that it performs extremely well. It gives us a very good solution, kind of world class. And the same thing goes for an energy network. So this is a social network, and on the right we have an energy network with weighted edges, weighted connections. And here this is this IEEE 33 bus case, which is basically describing some kind of a small size energy network in some, I don't remember what it was, in the United States, some data of some kind of transistors and stuff interacting with each other, connected to each other via transmission lines. And here again, the solution space is quite vast, but our the solver, typical solver, linear solver here is the so-called Gurobi, which is the state of the, let's say, art from the industry point of view. And D-Wave doesn't do, the quantum annealer doesn't do much better than that, but it turns out the Fujitsu digital annealer, which has a much higher degree of connections between the nodes, because of course connections are, I mean, it's not a quantum, it's just a digital annealer, it's just a numerical code, hardware. And our code are performing extremely well also. So this is kind of the take-home message, that this algorithm is interesting, and it gives an impressive performance on these kind of real-world problems. And so that gives us the motivation to pursue this problem further. The fact that we have used only our laptop so far doesn't mean that we shouldn't go further. But then we need to have access to supercomputers, and in principle, the best thing would be to have GPUs or parallelization on GPUs. So, and the algorithm is very well prepared for that. So we believe that that's an interesting and realistic direction to go. Of course, we want to address practical real world problems. So that would be very fun to kind of get into a bit of that. And but as a physicist, and I think it's also extremely interesting to look at this quantum versus classical. This is a different type of model than one typically is used to from D-Wave or other types of quantum simulators. So it would be very interesting to understand also the kind of interplay between exactly this bifurcation and chaotic or ergodic behavior, and kind of quantum quenches or quantum adiabatic behavior as we kind of know it from other systems. So thanks a lot for your attention, and I'm happy to answer your questions.
Thank you very much. I think I start with one question. Do you know have you studied some of the scaling of your algorithm with the number of degrees of freedom, like the number of nodes in your graph and so on? Do you have a feeling for this?
We haven't really done a very systematic. We have of course looked at max cut. So the max cut is kind of the easiest thing, because it's just there's no constraints, and you just look at you look at the Ising kind of terms, and we just saw that it is extremely fast and doesn't really. I have a table here. I mean, it takes 20,000 nodes within a few seconds. So I think there is a scaling behavior. I mean, it grows, of course, with time, but we haven't looked at the slope. We didn't look so much at the at the time it takes, but we have looked more on the quality of the solution. Yeah.
Okay. But with 20,000 nodes, I guess it's hard to know the optimal solution.
Yeah.
At least in general.
We can
Okay,
compute,
so are there...
yeah.
Yes, sorry.
Yeah, we can just compare to other benchmarks around there.
Yes, yes. Are there any more questions? If not, then thank you very much.
Yeah, thank you, Rest.